Okay, the problem that we're going to look at now is the preparation of a phosphate buffer with neutral pH. So that's pH 7.00. So these are the conditions that we're given. Neutral pH, our final volume is going to be 0.250 liters, 250 milliliters. We're going to have a total phosphate concentration of 0.226 molar. And we're going to prepare this through the addition of solid sodium phosphate plus the addition of a 1.00 molar hydrochloric acid solution. What we want to determine here is the mass of phosphate needed to prepare this buffer plus the volume of that 1 molar hydrochloric acid solution that we need. Now, it's important to recall that phosphate belongs to a triprotic acid-base system. So this is going to be different from the prior example that we looked at. Now, we refer to the phosphate buffer system as triprotic because although we are starting with phosphate itself, we could add either 1 proton, 2 protons, or 3 protons to derive the acid-base species that we need. So not only are we going to have to determine what the predominant acid and base are in this buffer system, but we're going to have to use the proper amount of our hydrochloric acid to stop in the proper space to get the proper buffer species. This titration curve shows the phosphate buffer system, and as you can see, it works in 3 different regions. Here in this low pH region, here in this middle pH region, which we'll be operating in, and then here it can also buffer in this higher pH region. So we're going to be starting over here with pure phosphate, and we're going to be really starting at this 3rd equivalence point here, and we're going to be acidifying it. So we're going to go past that midpoint, past that 1st equivalence point, and we want pH 7.00. So we're going to pass this midpoint, and we're going to settle here. So we are going to acidify beyond an equivalence point and beyond a midpoint. So within this buffer region here, we are on the more acidic point of the midpoint here at pH 7.00. So that means that we are going to have more of the acidic species than the basic species at this pH. So what specifically are the acidic and basic species that we should expect here? Well, it's not going to be the phosphate and hydrogen phosphate system that we started with when we began acidifying. We passed that 1st equivalence point and made it more acidic. And so this is going to be the acidic species within that middle region of the titration curve. And this is going to be our basic species. And since we're going to be below the pH seen at the midpoint, we should expect to have more of the acidic species than the basic species at pH 7.00. So let's use the concentration that we were given for our buffer system. We were told that our total phosphate concentration was 0.226 molar. And remember, that's the total amount of both the acid and the base phosphate conjugates. We were also told that our total volume was 0.250 liters. So we can determine the number of moles of phosphate that we have in there. Just moles equals concentration times volume. And so our total number of moles of phosphate in this buffer system is going to be 0.0566 moles. And again, remember, that's the amount of both conjugates present in our buffer. In answer at this point, the first question that we were asked, how much phosphate do we need to add? We have determined the number of moles of phosphate, so now we just multiply by the molar mass of phosphate, and let's assume that we're working with anhydrous sodium phosphate here. This is the formula weight for sodium phosphate anhydrous. This is our number of moles, and so we need a total of 9.28 grams of sodium phosphate to make our buffer. Now the next step is to plug the information that we do have into the Henderson-Hasselbalch equation. pH equals pKa plus the log of the amount of moles of base over acid. Okay, because then we'll be able to solve for that, and we'll be able to determine how many moles of each species we have in our buffer that we're going to need to acidify in the subsequent step. So plugging what we have pH 7.00 equals the pKa plus the log of this ratio. That's a lot of algebra going on there, and that might be a bit intimidating there to solve that equation. So I recommend that we're just going to call this unit here for now our ratio, y, okay, and then we're going to determine what that ratio is, and then we can solve for x. So here we just have the Henderson-Hasselbalch equation with the numbers that we know plugged in, our pH, our pKa, the log of our ratio, and we're going to subtract 7.21 from each side. We have negative 0.21 equals a log of y. Now you know that we can take each side here and raise it as a power of 10. And so 10 to the minus 0.21 equals 10 to the log of y. Now, an exponential and a logarithm are essentially inverse functions of one another. So 10 to the log of y is essentially y, okay, and 10 to the minus 21 is 0.617. So 0.617 is equal to, now let's plug in what y represented. Recall that from the previous slide. So our ratio equals x minus 0.0566. That's what we knew as our total number of moles, minus x. That's the amount of acid we have. This is the amount of our base. And solve for x. And so when we solve that, that's a rather straightforward algebra equation that we'll have then in our buffer solution is 0.0216 moles of the basic species, that's hydrogen phosphate, and 0.0350 moles of the acidic species. Now, we need these numbers here, not because we were asked for them specifically in our question, but we were asked for how much acid did we have to add to make this buffer. And so let's translate the buffer composition that we now have into the amount of acid required. So we know we've got this much of our base plus this much of our acid. Well, to make our base, we just need 1 hydrogen per phosphate unit. And so 1 mole of hydrogen ion per hydrogen phosphate. But to make our acidic species, we had to add 2 molar equivalents of acid. So we're going to take into account both the number of moles and the number of molar equivalents of acid to make each of these species. And so we're just going to apply that hydrogen count to our buffer composition. So for hydrogen phosphate, that number of moles times 1 equals that much acid. For dihydrogen phosphate, the number of moles that we determined times 2 for that, and just add them together. And so we see that we're going to need a total of 0.0916 moles of hydrogen ion. And so in a 1 molar solution, that number of moles is equal to that number of liters, or this many milliliters. So we're going to need 91.6 milliliters of our 1.00 molar hydrochloric acid stock solution. So now this is the summary of our final answer. We needed 9.28 grams of sodium phosphate, 91.6 milliliters of hydrochloric acid. We combine them in a volumetric flask, 250 milliliters, and just simply dilute up to that volume.